Okay. Now, what about let's see. What about question 7? We have the third clause now, which is defined as it says on in the problem sheet. Now, does the definition of the third clause make any sense? Okay. By the way, there's another small typo in question 7. Let's fix it. There's a missing parenthesis. Okay. Well, what it says is that we have minus the Euler clause. Minus 1 to the nth times the square of the Euler clause. Okay. Now does the formula from question 7 make any sense?
Before we had pullback of gamma, but this formula is for gamma itself.
Well, let's see.
Is it important?
Blah 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 blah. Well, pullback, yes, but let's see. Pullback on the well, actually, well, in a sense, it is important. Here we don't have the pullbacks, but my claim is that let's see the formula. Let's first of all let's do this formula for the pullback. Does the formula make sense when after taking the pullback to x?
So the statement makes sense.
Okay, the statement makes sense. Now, why is it true? In particular, why do I have minus 1 to some power? Откуда здесь берется минус 1 в степени что-то там, в степени L? Значит, объяснение такое, что, значит, что у нас иксы будут фигурировать, значит, каждый иксы будет фигурировать 2 раза. Один раз с плюсом, другой раз с минусом. Почему? Потому что у нас, значит, формула, там определение класса Тода применяется к прямой зуме, в которой каждый L-иты входит сначала сам по себе, а потом в виде сопряженного. Значит, поэтому у нас возникает минусы в таком же количестве, сколько было иксов. Да нет, понятно ли это?
Понятно, да.
Simon, let's replace Q. Sorry, let's replace gamma tilde with Q upper star of gamma tilde. Does the formula make sense then? The formula from question 7.
Actually, no, I haven't got how to prove this. Because, for example, this -1 to some power, I mean, how
Well,
is it there?
there are, you see, when we apply the definition of the dot class, there are as many xi's as minus xi's. Why? Because we have as many bundles li as the conjugate. As the conjugates of those bundles. Let's look at the formula. Q upper star of gamma gamma m tilde of c times c is L1 plus L1 conjugate plus blah 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 plus LL plus LL conjugate or dual.
I guess I got it. Yes. Now, because I thought we don't consider. Sorry, we do consider the dual bundles in third formula. So it doesn't have third. Okay, now it makes sense. Yeah.
Okay.
Everything's clear.
So this formula holds upstairs, meaning it holds after we split the bundle. Now my claim is it holds downstairs as well, and this is important. That's where we use the fact that the map Q induces an injection in rational cohomology. Vladimir, does this make any sense?
Not clear.
Yes. Sorry, do you mean here like there's Q of gamma m as well?
Well, I have the splitting. I have the map Q, which splits the bundle as a sum of rank 2 bundles.
Yeah, I just mean that on the problem sheet there's no Q. Is this a typo?
So before question 6 there is a Q, but in question 7 there is no Q. And this is precisely a consequence of the splitting principle. We are allowed to erase Q. So we'll first prove the formula with the Q, and then Q of the star is injective, so we have the same formula without the Q.
Okay.
Значит, Володя, мы доказываем сначала мы доказываем вот эту формулу для прообраза гамма-стильды при Q. Ну, и там мы доказываем, вот, значит, разобьем все на подраслоения ранга 2. Вот, но, значит, потом пользуемся тем, что со звездой инъективно. Поэтому, если что-то было верно, вверху, то оно было верно внизу тоже.
And sorry, what is E? Like Euler class of gamma, or?
E is the Euler class of gamma tilde. And the Euler class squared. Why? Because we have x1 times minus x1, x2 times minus x2, and so on. So we get each variable twice, once with a plus and the other time with a minus.
Okay, I think I understand now. Yeah.
Okay, Volodya, does the formula make sense now?
Yes.
Okay, so here comes the key trick. Question 8. it often happens. That the index of a differential operator, in fact, does not depend on the operator. The only thing we use is that there is an elliptic operator from this bundle to that bundle, and we don't need to know anything at all about this operator in order to calculate the index. And let's see why. Blah 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 blah. Okay, so I'll write this plot down. Suppose we have an elliptic operator, which means the symbol is an isomorphism. Sorry, what is P? P is the projection from there. It's not working. P is the projection from the cotangent bundle minus 0 to x. Okay, now suppose that all bundles, meaning EF and the cotangent bundle are all pullbacks of some bundles under the same map. and here calligraphic T is an oriented bundle, and the pullback preserves the orientations, and suppose that the Euler class is not a zero divisor. Euler class of T is not a zero divisor in the rational cohomology of B. And suppose also suppose also that the symbol is also a pullback. I'll explain what this all means. Well, here capital P is a projection from beautiful T minus the zero section to B. What does this mean? Well, this means the following thing. We have this isomorphism between P upper star of V to P upper star of F, and P upper star of V and this is given by the symbol. So we suppose that there is an isomorphism between P upper star of E to P upper capital P upper star of the calligraphic E to capital P upper star of the calligraphic F, such that the diagram commutes. Well, then. Then I have the element of the compactly supported K theory of X, which I need to know in order to apply the index formula. And I have sorry, I also have an element of the compactly supported K theory of T. And more precisely, in the index formula, I have CH of this element. Okay, now well, I have this diagram which commutes and the element in the lower left corner is what we're after for the index formula. Okay, so well, the first trick is we can do the computation. We can do the computation in the universal example, meaning in the K theory of T with compact support and then pull everything back. Okay, so this thing lives in the well, reduced cohomology of the Thom space of the bundle calligraphic T. Okay, now now I want to I want to apply the inverse of the Thom isomorphism. So I have the Thom space and the cohomology of the Thom space is isomorphic to the cohomology of B. Does this make any sense? Philip, does the word Thom space make any sense?
Yeah, it's quotient of disk by sphere bundle.
Yes, yes, exactly. So we have this large space B, and on it we have a bundle, a vector bundle, which gives us the cotangent bundle after pulling back. And I want to calculate this, and I use the Thom isomorphism. Okay. Now the well, this square commutes. Why? Well, because the Thom isomorphism is this square commutes, because the Thom isomorphism is compatible with fiber-wise isomorphisms which preserve orientation. Okay. Now we want to calculate. So in order to calculate what we're after, it suffices to and what we're after is the element in the bottom left corner. And the idea is let's calculate what's in the bottom right corner, and then just take the pullback. The pullback under what? Well, the pullback under well, let's call this map F. It deserves a name. And the pullback under F upper star. The element in the bottom right corner lives in the cohomology of B, and this one lives in the cohomology of X, which is the same as just the cohomology, because X is a smooth manifold, so it's finite dimensional, and there is no need to write two stars, one suffices. Anyway, the element tom to the -1 of blah 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 is actually easy to calculate, and this is basically what we do in a question in questions 8, 9, and 10. Okay, now question 8. What is question 8 all about? Well, question 8 is about constructing the element. Okay, I'll use another color. So this element this element sigma d, capital sigma d, is constructed in question 8. And B, in our case, will be B S O M. Now, tau, sorry, T, calligraphic T, in our case, again, will be gamma of n tilde. Now E will be lambda even of gamma m tilde tensor C, and F will be the same but for odd lambda. Okay. So in question 8, we construct an isomorphism between calligraphic E and calligraphic F. And this isomorphism is given by the same formula as for just the cotangent vector bundles, namely would take exterior product plus substitution. Now, does this formula make any sense? Saman.
I guess yes, it does.
Okay, Vladimir, does question 8 make any sense?
Well, the question makes sense, yes.
Well, but does the answer to the question make any sense?
Well, it makes some sense, but less the question
Так,
itself.
значит, смотрите, значит, у нас, все тянется с Гроссманиана BSO. Вот, ну, значит, что значит все? Ну, Там, во-первых, во-первых, все расслоения, а во-вторых, изоморфизм между значит, лямбда-четными и лямбда-нечетными. А какой у нас изоморфизм? Давайте вспомним. Изоморфизм устроен следующим образом. Мы берем, значит, изоморфизм зависит от кси. Вот это важно. Значит, кси это касательный вектор. Значит, мы берем значит, сначала внешнее произведение на кси, потом постановку на кси, потом плюс того и другого, и вот изоморфизм. Но те же самые фокусы можно провернуть в Гроссманиане. Значит, что это значит? Это значит, что там, имея там вот это вот лямбда четное минус лямбда нечетное в Гроссманиане, мы можем и какую-то ненулевую кси. Мы можем сделать то же самое, значит, то есть внешне умножить на кси плюс поставить кси, и что мы получим? Мы получим изоморфизм между, значит, лямбдами четными и лямбдами нечетными от чего? От, значит, гамма с тильдой на Гроссманиане. Ну хорошо, да, значит, изоморфизм будет зависеть от кси, который значит, будет не нулевым, значит, там, элементом уже того самого, значит, уже, значит, лямбды, то есть не нулевым элементом там, значит, расслоения гамма с тильдой уже на Гроссманиане. Вот таким образом, вот эта вот диаграмма, которая написана внизу страницы, она комментирует просто по построению. Вот таким образом мы получили, что мы тянем назад не только значит, не только все расслоения, а еще и изоморфизм между, значит, между полбеками вот этих вот расслоений. Okay, Philip, does this make sense? Does question 8 make any sense?
Like formulation, yeah. I think I just need to think about the last map.
Okay, so the gist is we not only we get all vector bundles by pulling back things from the Grossmanian, we also get an isomorphism between P alpha star and P alpha star by pulling back some isomorphism defined on over the Grossmanian. What does this mean? Well, this means that this diagram, which is at the bottom of the page, commutes. Okay, we're going to get kicked out of the session. So let's reconnect and then we'll finish talking about question 8 and maybe question 9, and then we'll have a break.